On the 6th of July, 1885, Louis Pasteur, a medical doctor and scientist, immunized a little boy who had been bitten by rabid dogs. Rabies at the time was a death sentence. Louis Pasteur had found a method to generate a vaccine, and after consultation with his colleagues, he tried it for the first time in this little boy. The vaccine was spectacularly successful and has saved millions and millions of lives ever since. And the good news is that the method he used to generate this vaccine we could apply to a number of vaccines which have been developed against viral infections. The bad news, however, is that there are some virus infections which are resistant to this vaccine development concept. And over the last 130 years, we don't have really developed any alternatives. How did Pasteur do this? Well, he took a virus out of a diseased patient, he grew it in a rabbit, and now the virus had to change in order to grow in the rabbit. It became weaker. It could not induce disease any longer. And therefore, upon inoculation into humans, it did not cause disease, but it caused an immune response. And this immune response then protected people when they were exposed to the strong virus, which actually made people sick. And so this concept of producing a weak virus by growing the virus in an animal or on animal cells, and then protecting us against exposure to the strong virus was successfully applied to very many viral infections, one of them measles. Here is a poster of the National Immunization Campaign, and after the introduction of the vaccine, case numbers dropped from 500 to 750,000 per year down to nearly not detectable. These days, we only see sporadic outbreaks of measles if parents choose not to immunize their children. Now, although this vaccine has been spectacularly successful, developing this vaccine has been a little bit like building a car for a smooth road. You know, it runs well, it's fantastic, it's comfortable, but what happens when the going gets rough? Well, we adapted a little bit and produced a motorbike. However, if we think about the tricky vaccines which face us today, we probably should change our mode of transportation. So maybe we want to develop a speedboat, or maybe even better, a plane. And what we do today is we produce cars, and then we're a little bit surprised that they do not fly. What we should always keep in mind is that viruses have been studying our immune system for millions and millions of years. And some of them have come up with very tricky and devious ways to get around the immune response. One of them is human immunodeficiency virus, HIV, which causes AIDS. That is a virus which can infect immune cells, it can destroy them, it can hide in them. And the concept that a weak version of HIV protects against the strong version of HIV simply doesn't work. It is a little bit different for influenza virus. As you all know, we're encouraged to be immunized every year. But that's a little bit like Russian roulette. You know, sometimes it works, sometimes it doesn't. And the reason is that influenza changes very quickly over time. And so sometimes the vaccine virus doesn't really match the strong virus we are exposed to. And you have to say, I was always a very curious child. I asked questions. I really wanted to understand the mechanisms. And when I was in 4th grade, my classmates called me professor. And when you call a kid names, you know, all sorts of things can happen. I became a professor. I'm very interested in how the immune response protects the body against invaders and how the invaders get around the immune system. And so my favorite villain virus, if you will, is respiratory syncytial virus, also called RSV. Respiratory syncytial virus, as the name says, infects the respiratory tract, so the nose, the trachea, the lung. And particularly lung infection is very bad for old people, for neonates and preterm babies. They might have to go to the hospital. They might even die. In adults, RSV infection leads to very severe bronchitis. After we overcome the infection, we are immune against the infection for a few years. Then immunity goes down, and we get reinfected. And that cycles over a lifetime. And the focus of my laboratory is to really understand these kind of things. And so we wondered if we compare measles vaccine, which induces immunity for a lifetime, with respiratory syncytial virus infection, which only induces a very short-lived immunity. What would be the underlying reasons? And in our animal model, we saw that measles virus induces a very good B-cell response. Those are white blood cells, which are very important for the immune defense. In addition, a number of genes which are important for the immune response were upregulated after vaccination with measles virus. They were not or very little upregulated after infection with RSV. And other groups have actually obtained matching results in humans, and so there's good agreement between the animal model and human studies. Now that RSV either stimulates very little or downregulates the immune response, we wanted to look more specifically at a certain protein of the virus. And that is the receptor binding protein. Every virus needs to enter cells in order to grow in cells. Otherwise, viruses die. And they use a receptor binding protein like a key. So they insert the key into the lock of the cell in order to be able to enter. And the key protein of measles virus induces very good antibody responses. Antibodies are proteins which are made by the already mentioned B cells, and they kind of smear around the key like chewing gum. So you have a key, chewing gum locks it, and you can't really insert it into the key, into the lock any longer, and that's kind of the concept. However, the key protein of RSV induces a very bad antibody response. In addition, this key protein is secreted by the cell, and it then acts like a messenger of the immune system. But what it actually does is it confuses the immune system. It's a little bit like you had a traffic light, it should be on red, but it really switches to green. You have traffic on the road. In a similar way, you have chaos in the immune system. However, there is some hope. Other groups have worked on a second protein, which is also necessary for the virus to enter the cell. So the virus needs a key protein, and then what I call the door handle protein, a protein which pushes down the door handle and then opens the door to the cell. And this protein, if it's produced as an isolated protein, actually induces a lot of antibodies. That is true for measles, but that is also true for respiratory syncytial virus. And so we and others have tested this protein in our animal model, the cotton rat, and we found that it induces a very good antibody response, and it actually protects then against infection with a strong virus. And so vaccine candidates based on this protein are now in clinical testing. What I've told you is that I think that understanding the mechanism, how viruses deal with the immune system, is really very important in developing advanced vaccines. And that obviously speaks to my interest as a scientist, to my nerdy side. On the other hand, I was reminded that life is not just science when a research associate in my laboratory received an email from a lady who works at OSU and had triplets. One of her children became infected with RSV. It had to be placed into an induced coma, and the child luckily survived. When she heard that we got funding with colleagues at Children's Hospital to develop a new RSV vaccine, she congratulated us and wished us all the best in our endeavors. And that story, to me, brought home sort of the human side of our work. Louis Pasteur was a pioneer at his time. And using his approach, all the sort of easy vaccines have been done. Nowadays, in order to tackle the tricky vaccines, scientists form networks and groups. And it is our hope that collectively we will be able to develop a successful RSV vaccine so that these guys and you all will not have to worry about RSV any longer. Thank you very much.